Good evening, my 11th standard warriors. Today is the second class of gravitation, and we are going to talk about the gravitational potential energy. We are going to solve problems on energy conservation, and we are also going to see how to escape Earth. And we will end the class with a problem where two planets are going to collide with each other. So, let's start this amazing session with all the lovely warriors who have gathered with full josh and full energy with their captain Shreyas, and I'm going live for all of you. And welcome to the Nurture series. This is a long-term series for all the 11th standard students. So if you are in 11th, or let's say you are in 12th and you want to clear your backlogs, or even if you are taking a drop and want to clear your backlogs, then yes, this is the right place you are at. And welcome to Enthuse. This is a dedicated English medium channel for all the engineering aspirants. So I am Shreyas. I've been training and coaching kids for a very long time and producing some amazing results, and I really hope I do the same with all of you. Hello Gokulnath, hello Dinesh, hello Ankit Saja, welcome Aishwarya, hello Harita. Nice to see all my regular warriors. Hello Chandan, hello John Paul, hello Kela Kirti, hello Jayvant, hello Ishpreet, hello everyone. Thank you for all the love. Hello Paulami, Pranesh. Okay, now I'm seeing all my students have become regular. That's really good. And I'm also checking out you are posting up the answers very regularly. I'm super duper proud of you because this consistency is very important. So even if you're watching this lecture as a recorded way, it's okay. Maybe you don't have time or maybe something is clashing. That's why you're not able to attend live. But at least make it a point that you watch all the classes, even if you're watching it recorded, consistently, and maybe after watching that class, make sure you post the answers in the comment section so that I know that you are watching my class in a recorded way, just in case. But live is always fun. So if you can make that time, and if there is no class which is clashing, please watch the lecture live. So if you want to know more about me, yes, do follow me on my Instagram handle. Yep. Glad to know, Harita, you're waiting, and even I'm waiting. Trust me on this. Yep. Let's light it up, Jayvant. Hello Mansi, welcome. Hello Bhumi, welcome Pranav. Hello OP Atul Gaming. And did you hear the news? Like KVY exam is postponed. And are you happy about it or are you sad about it? If you're happy, put a smile on your face and put it in the chats. And if you're not so happy about it, put a sad smiley over there. And if you're not giving any KVPY exam, just put a lol in the chat box, like you can laugh it out. Yeah, you can just laugh it out. Okay. Gokulnath, you can do one thing, just watch the or just check out the solutions in the Telegram group. If you still don't get it, leave a comment after that video and whichever video you had a doubt in, and I will definitely help you out with it. Okay, so there are lots of lols out here. Oh my god, look at that. Okay, so some smiles. Somebody is smiling with a blush. Oops. Samyukta also saying lol. Okay. So okay. A lot of smiles. Nobody's sad about it. Everybody's happy. Okay. So Mansi, I think some of the channels just got hacked and somehow we are safe. Some of the channels are safe. So we are looking into it. Don't worry. The data won't go anywhere. Obviously, the team is working hard to make sure whatever has gone wrong, it is going to get recovered. So don't worry, whatever channels have got hacked will be recovered very soon. Okay, we'll just wait for it. All right. So I think those of you who have not yet prepared for KVPY examination and maybe just have registered for it, most likely you should start preparing for it now because the exam will get postponed. And I tell you, this is the best opportunity. Plus, you can also simultaneously prepare for your CBSE Term 1 examinations, and you can start your journey with Vedantu in the Pro subscription. Reason is many of you have some kind of problem either in concepts, or you have nobody to solve your doubts, or you don't have the right material, or you don't have the mock tests, or you don't have the assignments, or you don't have the batches specialized for KVPY or CBSE or JEE or NEET. So if you're looking for something like a one-stop solution for all your needs, that too ghar baithe, that means sitting at home, then do consider checking out the link which is there in the description box, because that link will lead you to the pro subscription. It is like Amazon subscription. So right at your home, you will at your fingertips get access to quality content with the best teachers so that you can prepare really well. And there are lots and lots of material for each and every kind of examination, and you will be like amazed to see the quality of content. And if you're not happy, you can leave the subscription after a month. So I would suggest take the subscription for at least 1 month because it's very cheap, 1350 rupees. You might see it as 15 days only, but let me tell you that 15 days, alright, you will get extra 15 days when you use my coupon code SHHPRO. So use my coupon code and get that extra 15 days. So it will actually become 1 month and you will get it for 1350 rupees. Okay, so that's the smallest package and you get additional features on the higher ends. So let's start with gravitational potential energy. And if you have not yet subscribed to the channel and if you have not yet liked the video, please do that now, because now is the time we are going to need a lot of motivation and a lot of yos and lot of strength and lot of josh to begin the class. So let's get going. Chandan, you have already taken 15-day subscription for NEET and you're enjoying the class. I'm so proud of you and glad you are having this nice combo of YouTube and the pro subscription. I'm pretty sure your success is guaranteed now. Yep, Aman, definitely. We are definitely going to secure it and I'm pretty sure the IT team is on this. Okay, let's start. Now, see, what is potential energy? Potential energy is auqat, ability. Do you have the ability to crack IIT JEE? Yes or no? Well, then you have IIT potential energy. Okay, that's what it is. Do you have the ability to crack the NEET examination to go into a very good college for medical sciences? Well, then you have NEET potential energy. So that's what similarly you will have gravitational potential energy. Do you have ability to do work because of the gravitational force? If the answer is yes, then you have gravitational potential energy. Okay, Darshan, don't say no, you have it, maybe you're just not seeing it. I'll give you an example. Let's say I hold this pen on my hand. I'm holding this pen. You will ask the pen, let's say the pen could talk. Let's just imagine, hypothetically, the pen could talk to us. I would look insane, like I'm talking to the pen. If somebody is recording this, like, sir is talking to the pen, he's lost it. Okay, so I asked the pen, do you have gravitational potential energy? Do you have the ability to perform work? The pen will look here, there, up, down. It will be like, I can't move. I can't move anywhere. So maybe I don't have any ability to do work. But then I'll be like, wait a minute, you're not looking at the bigger picture. Maybe you're not able to do work because of something else. And that something else is nothing but my hand. Because I'm holding you, because I'm protecting you, that's the reason why you're not able to do work. If I leave my hand, obviously the pen is going to fall. And then the pen, because of the gravitational force, will gain kinetic energy. So gravitational force has done work on the pen. So that means what? Whenever something has potential energy, to check if it has it or not, you should leave it free. So do you have potential to crack IIT? Yep, let yourself loose, let yourself free. Don't have those constraints in your head. You will see that you will be able to crack JEE examination. So if there are some restrictions on you, it's like your hand holding this pen. The pen is you. You all have energy. Same with this pen has gravitational potential energy, my dear warriors. Okay, great. Thank you, Diva. Oh, I hope you will soon reach my live videos as well. Okay, glad you're watching my old videos too. Okay, great. Now, the thing with gravitational potential energy is, this potential energy comes because of gravitational force and it changes when you change the distance of separation between the masses. You bring them close, you make them go far away, the potential energy will change. And remember, I had given you this simple rule. Any system will try to become, from sadness, it wants to become happy. And sadness is always high potential energy and happiness is always low potential energy. If I give you now two situations, consider this as situation number 1. This is situation number 1. The second situation is when these masses are little bit close by. So this mass is here and this mass has come close by over here. This one over here is situation number 2. If I ask you, in which situation is the potential energy more? Is U1 more than U2? Is U2 more than U1? Or is U1 equal to U2? Which symbol will you put over here? Think carefully. Think in terms of happiness, think in terms of sadness, you will get the answer. What do you think? Yep, Zayed, you put it rightly in the form of smiley. Yep. Hello Chitra, join in. Yes, I know that. Chitra, don't worry. Things are being taken care of. IT team is on it. Okay. Diva, even if you are in 12th, it's okay. You have time, bacha. Don't worry about it. You will definitely cover up everything. Okay, if you practice and be with me systematically till the end. Okay, by January, February, you will be done. Okay, is U1 more? Is U2 more? Or both are equal? Think who is more happy, who is more sad. Just think, both of them want to be together because of the gravitational pull. They want to be together. When you separate them, what is their bhavna? What is their feeling? What do they want? Think, what do they want? They want to be together. When they are together, they are very happy. When they are sad, they will be far away. Think this way. That means U1 will be more than U2. Done, dana, done. Correcto. Don't worry, Chitra, everything will be taken care of. Yup. Is that understood? That's how you can attach emotions, attach feelings and figure out which has more potential energy, which has less potential energy. Alrighty. So, masses which are separated by certain distance have the ability to move because of the gravitational force, and that means they have ability to perform work. That is reflected as the gravitational, that ability to perform work is reflected as gravitational potential energy. So the gravitational potential energy at any point is defined as the work done in bringing that object from infinity to that particular point. Okay, we are going to derive that expression for gravitational potential energy, but this is the textbook definition which you should know. Gravitational potential energy is the work done in bringing that object from infinity to that particular point. Now, whenever we talk about gravitational energy, remember we should always talk about the zero reference. Every time gravitational energy or any potential energy is always measured with respect to something. Zero has to be set. That bar has to be set. Now usually you used to take the Earth's surface as zero energy or the starting position as zero energy. But when we talk about planets, stars, suns, moons, etc., the moon is never going to be on the surface of Earth. The sun will not be attached to the Earth. So we cannot make the surface of any planet or star or any such body as zero energy. So we take something else as a standard zero reference, and that standard is infinity. It is infinity. Yup. So when they are infinitely far away, very, very far away, their gravitational force is negligible. It's like that mass cannot see the other mass. It hardly can see it. It's very, very far. The force is negligible. You leave them freely. They'll be like, okay, there's hardly any force. I'm not going to go there. There's no force. I'm just going to stay there. They have no ability to do work. So that is zero reference when the separation is infinity. Keep this in mind. So when they are separated by infinite amount, then the gravitational potential energy is taken to be zero. Keep this in mind. Zero reference. Now comes the critical part. Okay. Just tell me this. If at infinity, I tell you the potential energy is zero. Now if I bring those masses close by, okay, this mass is close by the other mass. Okay, there is some separation between them. Okay, this mass is now close by. There is some finite separation between them. Will this potential energy be more than this energy? Or will it be less than this energy? Think about it. Will the potential energy, when the separation is R, will it be more than, less than, equal to the potential energy at infinity? Think about it. It's very easy. Just think about happiness and sadness. You will get the answer. Yep. Yep. Like the attractive force on coconut or coconut tree on me. I hope Suchi Mama No coconuts fall on you. It's very painful. Trust me on that. Okay, Roshni says less. Hi Dayani, Vijay, welcome aboard. Hello Bhargavi Bhaskar, welcome. Join in Bachalo. Good evening. Let's see what your answer is. Harita says lower. All right. Polar system, yes, partially you can think of it. It will be it has already been taken care of in circular motion. I gave you a brief idea about it. You'll also learn it in what do you say, conics and all of that. Yep. Less, more. Okay, it should be less. Makes sense, because when you take them far away, they become sad. When they come close, they become happy. That means it should be less. But we all know that the potential energy at infinity is 0. So that means you are is less than 0. Correct? If you are is less than 0, that means you are is going to be negative. So that's very, very crucial. Gravitational potential energy formula will always be negative. Keep this in your mind. Embed this in your head. Let it register in your head. It might take some time, but remember, gravitational potential energy for all finite distances will be a negative value. Like, sorry, it's not making sense. See, it's negative with respect to infinity. When you are at infinity, it is 0. When you are close by, then it is lesser than 0. So what is the number which is less than 0 called? It is negative number. So that's why gravitational potential energy is negative. Is that clear? Everybody clear about this? Okay. Hello Molesh. Welcome. So keep this in mind. So what is the formula for gravitational potential energy? Here is the answer. You can try it out at home as well. It's very easy, but I'll give you the concept behind it. Remember, I had told you du is nothing but minus work done by that conservative force. Remember, we have done this in work, power, energy chapter. du, the change in the potential energy, is the work done by the conservative force. In this case, the change in the gravitational energy is the negative of the work done by gravitational force. So when you do this, work done dw will be force dot dr vector, and when you integrate this, so when you integrate this with proper limits, what are the limits? Think, when my r, which is the separation, is infinity, then my potential energy is 0, because that's my reference. Remember, for infinite separation, potential energy is 0. When my separation is r, that time my potential energy is u. So if you put these limits, the final answer that you get is u is equal to, oh by the way, that force will be gmm by r, your r square, which is your standard gravitational force formula, correct? So F is gmm by r square. Now the final answer that you get is minus g m1 m2 divided by r. So this is the standard formula which you should remember. Interesting thing to note, it is negative. It, like I just said, it will always be negative. Is that clear? Very good, Gogulnath. Hello Philson, welcome aboard. Yep, yes Tanishka, it is hacked and the IT team is working and it will be recovered. Don't worry, nothing will be lost, okay? It's not so easy to, just screw up all the data. Don't worry. Yep. So Srivartana, I have already mentioned the KVPY expected dates. Just watch my 4-minute video. I have just posted it some time back. Just watch it. You will see my opinion on when the KVPY exam will be. Alright, bacha? Great. It is like KQ1, Q2 by R. Exactly. Did you know that there are 3 lost brothers? You might have heard some stories. There were twins. They got separated. And finally, suddenly they realized, oh, if you pinch me, then that guy also gets pinched. If you get slapped, that guy also feels the pain. If you feel hungry, other guy also feels hungry. And then they finally understand, oh, we two are brothers and we were lost in that mela. We were lost in that fair when we were kids. So there are not just 2 brothers, but there are 3 brothers over here. And who are the 3 brothers? Well, the 3 brothers over here are, number 1, Gravity. Gravity is one guy. He is the twin, or rather a triplet, of statics. So you have electrostatics. So you can see they both look identical. Very, very similar. And there is one more person, and that is magnetism. So you have magnetism. They also have similar formulas. In magnetism, instead of Gm1m2 by R, you have mu naught by 4 pi, which is a constant magnetic poles ka product divided by the separation. It's very, very simple. Yeah. So there are three brothers. If you study one, you know the characteristics of the other, you know the characteristics of the third one. You study any one chapter. So this is generally studied in 11th. You study these two in the 12th standard. So this lays your foundation for the 12th standard. Keep this in mind. All right. Let's move ahead. So the formula is minus Gm1m2 by R, and that's always going to be negative. The negative sign shows that the gravitational potential energy decreases with the increasing distance. Great. Chalo, let's start solving some questions. And here is the first question for all of you on your screen. Welcome, Swarlina. Good evening. Yep. Swarlina always has an entry with a blue heart. Thank you. Hello, Sashi Varun. Welcome aboard. Yep, Gokulnath. It is Coulomb's law. Yep, there are triplets, Vignesh. Glad you guys got it. Okay, no problem. Even if you are late, you can catch up. You can catch up at 2x speed. You can rewind back the session and watch the replay in case you miss something. All right. So here we have. So Shrivashika, good evening, bacha. Think about this question. You have a mass on the surface of the earth. You slowly start taking it up. So you take it till the height of Mount Everest. Then you take it even higher in the sky. Then you take it outside atmosphere. Then you take it really far away outside our solar system. So in this process, how do you think gravitational potential energy will change? What do you think will happen? Will it just increase? Will it increase and then decrease? Will it decrease and then increase? Will it remain constant? Will it decrease? Or will it increase, decrease, then increase? Or will it decrease, increase, then decrease? So many options. Think, what do you think will happen to the gravitational potential energy when you slowly start taking it up? Will it increase? Will it decrease? Will it increase, decrease, decrease, increase, remain constant, increase, decrease, increase, decrease, increase, increase? What do you think should happen? Okay, come on, my warriors, think about it. It's not that difficult. Attach bhavna. Remember the bhavna method? Remember the feeling method? So attach feelings, attach the bhavna to the question, you will get it. Okay. Increase from negative to 0, says Paul Nimi. Chandan says only increase. Kamlesh says 0. Roshni says increase. Tamil A says it remains constant. Interestingo. Let's see what the correct answer should be. Negative to 0, says Atif. Good evening, Gokul DV. Join in Bachalog. Welcome aboard. And let's see what the answer should be. Okay, let's attach some feelings. What does the mass want to do? Obviously, that mass wants to stay as close as possible to the earth, because that's where it will be very happy because of the gravitational pull. So the mass, actually speaking, will be very, very happy. It will be crying with laughter over here. When you take it up, it's going to laugh maybe, but not so happy about it. When you take it even more up, it's going to start frowning. And when you start making it go more up, it's going to become more sad, because gravitational pull is down. You are making it go against gravity. A lot of people think, sir, as I go up, then the gravity will reduce. So if the gravity reduces, sir, then what should happen is the potential energy should also decrease. Let me tell you, as you go up, gravitational force will reduce. Acceleration due to gravity will reduce. But it will still be taken against gravity. So when you move the object from here to here, maybe the potential energy increases by 10 joules, because the gravity is very strong, very close to the earth. But when you take from here to here, because the gravity has fallen, it's not so much, potential energy will still increase, but not as much as before. So it might be less than 10 joules, maybe 8 joules. When you take it from here to here, it will still increase, but maybe not 8 joules, maybe 5 joules. So it will keep on increasing. It will become even more sad. It will start crying. Here though, it will start crying from both the eyes. It will have, lot of tears. Yeah. So it's going to become more sad. So that's why potential energy will just keep on increasing. So potential energy just keeps on increasing. But the rate of increase of potential energy is decreasing. See, if you understood the statement, I will repeat myself. The rate of increase of potential energy will decrease. Whatever potential energy was increasing, it won't increase so much because gravity will become weak and weak. It won't increase so much. Is that making sense? Is that making sense? Yep. Hello Henry, welcome. Churchalpur. Oh my god, where is this town? Okay, just let's continue. Yeah. So Mangalam will have 3 sessions. We'll have 3 sessions for this session. Okay, so it will be negative. Yes, it will become less and less negative as you go away, and at infinity it will become 0. So from -10 it will go to -9, -8, -7, -4, -2, -1. Finally it will tend to 0. So it will basically increase. Okay, so let's move on to the next question coming up on your screen. Here it is. Figure this out. Come on, my warriors. Okay, so here we have a question where which of the following represents potential energy of the 2 masses as a function of distance? Figure this out. Come on, think carefully. Which of the following represents potential energy of the 2 masses as a function of distance? You take the 2 masses, change the distance. How do you think potential energy will change as a function of distance? Figure this out. Come on, think about it. Come on, my warriors. Just 1 second, my warriors. There is one small trouble. Just keep on solving the question. I'll just come. Just 1 second. Okay, yep. So all of you are saying D for sure. Is it? Okay. Let's see whether the correct answer should be D or not. Okay, I think most of you are correct. Very good, my warriors. I'm proud of you. And the reason for that is this formula. U is equal to minus G M1 M2 divided by R. So as R increases, what will happen? This number will reduce. That means when R increases, it will become less negative. So it has to first of all be below the horizontal line. So option B and option A are ruled out because it is on the upper side, obviously. So one of them must be correct, but it can't be a straight line. Why can't it be a straight line? The reason why it can't be a straight line is because R is there below. So whenever you have R below, it will not be an equation or a function of a straight line. It will be a curved line. So that's why, yes, it is option D. Perfecto. Let's move on to the next one. Now, let's talk about calculating potential energy of bigger bodies, smooth bodies or continuous bodies. How to do that? There are simple ways to do this. Imagine there are multiple masses M1, M2, M3, M4 and you want to calculate the total potential energy. There is a simple way of doing it. What do you need to do? See, these two masses, M1 and let's say M4, will have some potential energy, let's say U14, correcto? They both will have some potential energy, let's say U14. M1 and M3 will also have some potential energy, let's say U13. Similarly, M2 and M3 will also have some potential energy, U23. M4 and M2 will also have some potential energy, U24. Then M4 and M3 will also have some potential energy, U34. And M1 and M2 will also have some potential energy, U12. So all the combinations. So if you have many point masses, try out all the combinations of all the masses. The total number of combinations possible is n into n minus 1 by 2. Does everybody know this? Do you know this simple formula? If you have n points, okay, which are all non-collinear, you can join them with, you know how many line segments? Guess what? You can join them with, you know, n into n minus 1 by 2 line segments. Yes, NC2. Basically, it comes from permutation and combinations. So you will have those many terms in the potential energy. That's all. As simple as that. So G M1 M2 by R, G M1 M4 by R, G M3 M2 by R. So all the terms will add up as simple as that. Is that clear, my warriors? Very easy. We are going to solve a question on that, but I just wanted to make sure that this idea is embedded in your head. Okay. Now comes the next concept. What if you don't have point masses, but you have a continuous body like this? Let's say you have a continuous body like this, then what will you do? For example, this is a mass, capital M, and there is a mass over here, let's say small m. You want to find the potential energy of these two bodies. You'll be like, sir, what is the catch here? I am not getting it. What is so different in this problem? You'll be like, sir, I know what to do. I'll take the center of mass and solve the problem. Nah, you cannot do that. You cannot assume the entire mass to be concentrated at the center of mass and then you'll be like, sir, I know the distance between these two is something and I'll solve the problem. If you do that, you'll for sure get a wrong answer. Do not ever try that. What you need to do is divide this m into small masses. Each of that small mass will be, let's say, d capital M, and the separation between them will be some variable, let's say r. Now the potential energy between these two masses will be minus g small m then d capital M divided by that variable which is r. This will be the potential energy du. This is the potential energy between whom? M and dm. So the total energy U between M and the total mass will be, basically take all the dm masses and try out all the variations, basically m with this, m with this, m with this, m with this. So all the sum of potential energies, integration, yes, summation. So G is a constant, small m is a constant. So we'll have integral dm by r. That's it. That's how you need to do it in case of continuous bodies. Is that clear, my warriors? So use integration. That's it. So see, you're getting a hang of integration now. Earlier when you learned about integration back in basic maths and kinematics 1D, you were like, what the hell is integration? But now you have started to at least guess, sir, integration is going to come. Whether I can do that integration or not, that's a secondary thing, but at least I can guess whether integration is going to come or not. That's a better thing, I would say. Okay, so whenever you have a continuous body, remember you're going to use integration, and okay, don't worry about these symbols. Use my formula. It might look scary over here and things might look very different. Just ignore this. I'll make sure that this is corrected. Okay, so just ignore this. I'll get it corrected. Okay, so let's solve a problem based on continuous bodies. And one such problem is of a ring. Find the gravitational potential energy of a ring of mass m with another point mass m. I think that point mass m was missing over here. That point mass m is here. This is x. We want to find this out. How much is the gravitational potential energy? Let's try this. Okay, what did I just tell you? Whenever you have a continuous body, divide it into small parts, dm, dm, dm. So let me divide that. So one such dm mass, let's say, is over here. Okay, I'm showing it in an exaggerated way. So this is dm, and this dm is at some distance from this mass. How much will that be? Oh, I can see a right angle triangle. Do you see a right angle triangle, my warriors? One side, 90 degrees. So how much will this be? Obviously use Pythagoras. So this will be r square plus x square. Very cool. Then there will be so many other dm masses. Can you see that? There will be one more dm mass here. So this length, one more dm mass here. So this length, one more dm mass here. So this length, one more dm mass here. So this length. You can see all these dm masses are at, in fact, the same distance from this mass, and together I have to find the potential energy. Let's try this. What will it be? So the total potential energy will be integral of du. Du itself is minus g small m d capital M divided by that distance, which came out to be root r square plus x square. The best part is that r is a constant, x is the constant. Why? Because remember, this distance is fixed. So all the points, all these green lines that I have drawn are basically on the curved surface of a cone. It's that hypotenuse, and these hypotenuses are same. So yep, all these distances are same. So this is a constant. A lot of you might have got afraid thinking, oh my god, I have to integrate this. You don't have to integrate this. In fact, small m, g, this minus are constants. They just come outside. So minus g m divided by root r square plus x square integral just dm. Now what is integral dm? What is integral dm? It's nothing but dm plus dm plus dm. All the masses being added. It's just the total mass. So it will be minus g small m capital M divided by root r square plus x square. So that is the final answer. Done, done. So it looks scary at the start. It looks as if you have to do some complex integral, but because all the points were at the same distance, you didn't have to actually perform any complicated integration. So it was very straightforward. Correcto. Yes, Chitra, your chat is visible. Don't worry. Yep. So remember this very interesting formula. Anyways, I have put it up for all of you again over here. Okay, let's solve another question. There are three particles. Each of mass m at the corners of an equilateral triangle whose side length is L. The work done to increase the side of that triangle to 2L is how much? See, why do you have to do work? Think about it. Earlier, these three masses together will have some potential energy. When you increase the side, you are going against their will. They don't want to be far away. They want to be together. So when you increase the side, you are making them unhappy. So you have to give them some incentive. That means you have to do some work to push them apart. So how much work did you do? Calculate initial energy, calculate final potential energy. I'm pretty sure you'll be able to get this, my warriors. Come on, figure this out. Think about it. Come on, my warriors. What will be the work done, okay, to move this out? Okay. Meanwhile, I'll start solving the question slowly. See, when they are at a distance of L, okay, so when they are at a distance of L each, this mass will have potential energy with this mass will have potential energy with this will have potential energy with this. So 1, 2, 3. 3 terms you will get. So my initial potential energy will be minus G m1 m2 divided by distance, which is L. Now I'll get 3 terms exactly like this. So minus G m divided by L minus G m divided by L, which is nothing but minus 3 G m squared divided by L. This is my initial energy. If you ask me what should the final energy be, I think I don't have to sit and calculate this again, because instead of L, now the separation is 2L. That's it. So wherever you saw L, replace it with 2L because the masses are still the same. So just you can write it as minus 3 G m square by 2L. That's it. Now the last thing is energy equation. This system had some initial energy, correct? You gave it some work. You did some work on it. So that's why it got some final energy. And that final potential energy is higher. Remember that. You did some work. So that's why you're able to push them apart. You made them unhappy by providing some work. So just substitute everything and you'll get W is equal to UF minus UI. So UF is minus 3 G m square divided by 2L minus initial. initial is this one. So minus 3gm square divided by L. So you can clearly see 3gm square by L is common. Minus minus is plus. So 1 is common from here. 1 minus 1 by 2. 1 minus 1 by 2 is half. So this will become 3gm square by 2L. And is that answer there? Yep, it is. 3gm square by 2L. That's the answer. I hope this is clear. Excellent. Very good. Many of you said B option. I'm so proud of you, bachalo. That's how you solve questions on work done against gravity. Now, last lecture, we studied shell theorem. Quick recap. What was shell theorem? When you're outside a shell behaves like a point mass. And when you're inside a shell, the net field becomes zero because all the forces from everywhere cancel out. That's what shell theorem was, but that was for forces. You can extend the same thing for energy, but there is a small catch, and I'll tell you what it is. First of all, if you have a shell and you are outside, okay, first let me mark all the parameters. This is mass m, this is radius, and this is the distance, this is the radius. At this point, you have some mass m. When you are outside, that situation is very much similar to this one, where you concentrate all the mass of the shell at the center. So the entire mass of the shell is concentrated at the center, and you are still at the same distance r, and now you just have to find the potential energy. What's the potential energy between two masses? Well, that's straightforward. So minus g m divided by r. So the radius has no role to play. So you can assume all the mass to be concentrated exactly over here. That means if I have, for example, a solid sphere, okay, imagine if I have a solid sphere. So I'll just mention it over here. This solid sphere is nothing but a combination of small shells like this, and each shell one can assume to be concentrated at the center. So if the solid sphere has a mass of m and you have placed a mass small m here at certain distance r, then this entire solid sphere, which is made of like onion like shells, onion is made of shells one over the other, you can assume it to be concentrated here, and it is just separated by the same distance, and the formula will still remain the same. Yep, as simple as that. Yep, correct. So when you're outside, you can just treat it like a point mass. Is this theorem valid for cubes or cones or rings? Come on, my warriors, let me know quickly. If you have a cube, if you have a cone, if you have a ring, if you have a disc, can you assume the mass to be concentrated at the center and then solve the problem? Very good. Correcto. Those are my warriors. Excellent. My warriors got it. Yes, you cannot use it for anything else. You can only use it for shells. Perfecto. Perfecto. What happens when you're inside? I don't know, Sriram, why I'm so cute. Maybe you should tell. Okay. How would I know? Okay. Now, when you are inside, what happens? What do you think the answer should be when you're inside? Okay, let me just mark the parameters. I'll just turn back and let's see what your answers are. You are at a distance small r from the center. This is your radius, capital R. This is the mass of the shell, and at this point you have placed a mass m. What do you think the potential energy should be? Well, it's going to be very interesting. Very interesting. Okay, you take another mass m, not inside. Okay, I'm just doing that. Yeah. Below small sphere taken, sir, matlab, I'm not sure what you mean by that. So right now you have a shell. Shell is hollow. It's a hollow sphere. Inside a hollow sphere you have kept small m in that empty space. So what do you think the potential energy of the system is? Yeah, that's what it is. So Divi is saying we should take the radius as r minus p. Okay, I'm not sure what you mean by that. Why r minus p? What is p over there? Okay, or rp? Okay, you can do that. You can take our radius as rp as well. Okay, chalo, think carefully. Roshni says 0. Lot of you might be thinking 0. A lot of you might be thinking, sir, force is zero, energy is zero. No, that's not true. Okay, now I'll prove this to you. See, just imagine you have a shell. It's a small opening. It's negligible, just so that that point mass can go, so that nothing actually changes. Now, imagine that point mass m is outside. Obviously, this entire thing behaves like a point mass. Correct? The entire thing behaves like a point mass. And there is some potential energy. And there is also some force acting on it. Now, when this mass comes here, still there is some force acting on it. But the moment this point mass comes inside, anywhere, here, here, or anywhere else, this force will become zero. Everybody agrees to this? Anywhere inside, the force on this small m will become zero, but anywhere outside, the force will be there. Now, you all have learned one rule, one theorem, one property, one formula in work power energy. And what was that property? It just said minus du by dr is equal to F. Haven't you learned that? Yes, minus du by dr is F. Potential energy curves, PE curves. F is minus du by dx. You would have learnt it. Negative gradient of potential energy. That means if by chance F is 0, where in this case, that means du by dr, the negative of that will also be 0. That means du by dr is 0. That means u is, carefully answer this. If du by dr is 0, if the derivative of u with respect to r is 0, that means u is, think carefully, what is u? U is, come on, perfecto megna bk, excelente. It is constant, correct. So it will be constant everywhere. But you will be like, sir, it could be zero constant also. Everywhere it is zero. But hold on. Just hold on for a second. I just know one thing. Everywhere it is constant, correct? So what do you think is the potential energy at the center? Let's just calculate it. What is the potential energy at the center? Let's just quickly draw this. You have a point mass m. This is capital M. This is a shell. Now remember, all the points are at the same distance from that point mass. All the masses are at the same distance from the point mass. Everybody agrees with this? Everybody agrees with this? This point mass is at the same distance from all the point masses. That means, think what will happen. The potential energy formula will be minus G m by r. This is like the ring problem. This is like that ring problem where all the masses are at the same distance. So you just take it as one single mass m. So since all the point masses on the shell are at the same distance r, so I can just take it as minus gmm by r. R is the radius. Problem sorted. So this is the potential energy at the center. This is the potential energy at the center. And just now I proved potential energy is constant everywhere. If potential energy is constant everywhere, that means U will be minus gmm divided by capital R. This is very, very crucial, and it is a constant value, like you can see, because R is the radius of the shell, not the distance from the center. Is that clear, my warriors? Think about it. Give it a moment and get a feeling out of this. Okay, perfect. Acceleration due to gravity is 0 at the center. It will be in fact 0 everywhere if it's a shell. Okay, so that's what it is. Inside, the gravitational potential energy is constant throughout, and it is same as that on the surface and same as that on the center. Okay, let's start solving some questions coming up on your screen right now. If g is the acceleration due to gravity on the Earth's surface, the gain in the potential energy of an object of mass m raised from the surface of the Earth to height h, or the height equal to the radius r of the Earth is how much? Come on, think about it, my warriors. So you have taken a mass from the surface to a height which is equal to the radius of the earth, how much do you think is the gain in the gravitational potential energy? Let's try and visualize this first. What is happening? So first of all, you have the earth. This is radius r. The earth's mass is m. And then you had this mass which was over here. And what you have done is taken this mass even further up by a distance of r, and you have placed it over here. So what is the change in the energy? This was initial, this was final. Think carefully, my warriors. What do you think will be the answer? G is acceleration due to gravity. Okay, let's start it step by step. The question is, what is the gain in the potential energy? So that means we have been asked, what is final minus initial? What is the final energy? This mass is here. This entire earth can be concentrated at the center of the earth. So basically the distance between small m and the entire earth's mass will be 2r. Can you see that? Because earth can be assumed like a point mass at the center by using shell theorem. So it will be minus g m divided by 2r minus. So this is final energy minus initial. This point mass is at a distance r from the center of the earth. The entire earth can be assumed like a point mass. So again at the center, so it will be minus g m divided by r. So that's it. Just need to figure this difference. So minus minus becomes plus. So g m divided by r, and you will have 1 minus 1 by 2, which is half. So it will be g m divided by 2r. But this answer is nowhere close to what is given over here in the options. So we need to do some modification. Last lecture I gave you this. Gm by r square is small g. So I can do that. How? If I want r square here, I need to multiply it by r. This small m is outside. This 2 is not even there in the formula. So this and this is the same. I've just multiplied and divided it by r. Now this is simple. This is nothing but small g. This is just r, this is m, and this is 2. So mgr by 2, which is option B. Done, done. Yep, very good. Looks like David was quick to answer. Very good, Thunder Skull. Very good, Dinesh Swarlina. Excelente, Polmi. Harita Chandan. Excelente. Perfecto. You got it. Moving on to the next question. A shell of mass m and radius r, come on, this is a simple one, has a point mass m placed at a distance from the center. The variation of the gravitational potential energy with distance r is correctly represented by which of the following curve? There is only one curve which represents gravitational potential energy as a function of r, where r is the distance from the center for a shell. So you have a shell, and then think about the different distances that you place the mass. You slowly increase the distance, and then you slowly bring it outside. Come on, there is only one graph which will satisfy it. Slowly increase the r. How do you think the gravitational potential energy is going to change? David saying B. Okay, very good, Suchi. If you have solved it with me and you understood it also, proud of you. Good, keep it up. So somebody is saying B. Okay, is it true? Paulmi also saying B. Swarlina also saying B. Yep. So first of all, the answer should be negative for sure, because it is gravitational energy. So always it is negative, number one. Number two, whenever you are inside, so whenever you are inside, it is constant, and that too it is a negative constant. If you look this graph, obviously it is not a constant. This is not a constant. Here it looks like it's missing, or rather it is over here. I know it is not 0. This is constant, but it is definitely not a 0. So obviously option D also goes. Here it is definitely a constant, and once you go outside, then the formula itself changes. It will just become minus gmm divided by r. So it will go like this. So when r increases, it will become less and less negative. So when r increases, it will become less and less negative. You can see this is negative side. It will become less and less negative. As simple as that. Yep, option B, correct. So moving on to the next one. Okay, before going to the next concept, let me tell you, if you want free mock tests, if you want lots of tests which will help you diagnose where your weak points are, Vedantu is giving you lots and lots of mock tests for your preparation. There will be 2 all India level mock tests, 3 practice tests for NEET, 4 diagnostic tests and 9 micro tests. And these tests are free of cost. All you need to do is go to the Vedantu app, download it basically from the App Store if you don't have it, and then enter your details like the login details, enter your mobile number, you'll get OTP, etc. There are different tabs on your mobile app. Go to the test tab and you will automatically see all the diagnostic, micro tests, all of this which you can prepare. It will give you a detailed report card of where you lack, where do you need to prepare yourself. Every aspect of the JEE and the NEET examination will be given to you. So make sure you take these tests and it will help you diagnose your problems. Okay, it's all free of cost. It's there in the link which is there in the description box below. Cool. Now let's talk about the last concept, which is escape velocity. Someday you get very angry. Let's say Pandu gets very angry one day and he's very unhappy with Champa. Okay, so there is Pandu. They both are over here. So this is your Pandu. Pandu is very unhappy with Champa because Champa is not listening to Pandu. Okay, Pandu is like, I want to go to Kashmir. Champa is like, no, I don't want to go to Kashmir. I want to go to, I don't know, she wants to go to the northeast maybe, or she wants to go to Andaman. They're very angry, they're fighting with each other. Pandu is like finally like fed up. I don't want you. I don't want to see your face. I don't want to see you on the surface of the earth. So what does Pandu do? So Pandu, his hands are long, okay. It looks very weird, but yeah, Pandu holds Champa and he throws her off. So Champa is thrown off from the surface of the earth. Pandu does not want to see Champa anywhere near him. That's it. He just says bye bye, tada, forever gone. So Champa is launched in the orbit and she goes to some other solar system or other galaxy or other, I don't know, planet. God knows what happens. So if Pandu wants to throw Champa so that Champa never returns back to the earth, because if he throws her with small speed, obviously Champa will go like this and Champa will land somewhere else on some other Pandu's head, and now it is somebody else's problem. So some other Pandu will be like, oh, I got a Champa from the sky, and he'll be like very happy about it. I don't know. So if you do not want Champa to re-enter back to the earth, you don't want Champa to do a projectile motion, okay, so you want Champa to permanently fly away, you need to throw her with a particular speed, minimum speed, and that speed is called as the escape speed. Yep, you need to throw with escape. You want to escape. Sometimes Champa wants to escape. Pandu is very torturous. Champa is like, you just throw me, man. That's it. I'm fed up of you. I just want to run away. Like, yeah, fine. Cool. So what is that escape speed? And that's the speed with which our satellites, our rockets are projected so that they do not enter the Earth's atmosphere back again, because you want them to enter into the gravity-free space where they can roam around freely. So what is this escape velocity? So let's figure this out. First of all, let's say you are projecting something from the surface. Okay, so you are, I'll just write it from beginning. So you are projecting from the surface of a planet. Interesting. Now when you project it from the surface of the planet, it has some energy, maybe kinetic energy, potential energy, whatever. When it goes far away, kinetic energy might change, potential energy might change, but the total energy will remain the same. Reason, mechanical energy conservation. So maybe potential will get converted into kinetic, or kinetic will get converted into potential. The total sum should remain the same. That means when you go really far away, very, very far away, that time all the energy which you used up, which was there initially, will still be there at a large distance. That is, when you're very far away, basically you have technically escaped. You have escaped the planet's gravitational pull. Very, very far away, infinite distance. So when you're on the surface, what kinds of energies are there? You will have potential, you will have kinetic. When you're very, very far away, what kinds of energies will be there? You will again have potential and you will have kinetic. What do you think will be the potential energy on the surface of a planet? Well, if you're on the surface of a planet, you are at a distance of r, which is the radius of the planet from the center of the planet. So the potential energy will be minus G capital M small m divided by r. Everybody getting it? So if you have a mass, it will be at a distance of radius of the planet where the entire planet's mass can be assumed to be concentrated. Correcto? Very good. Now, what will be the kinetic energy? It will be half mve square. What is that v? It is the escape velocity. So escape velocity, escape speed, whatever you want to call it. So it is the escape speed, that speed with which you should just throw so that it reaches very, very far away distance. Now, you go very far away, infinity. When you go to infinity, the potential energy will be 0. Correct? And when you go so far away, you'll be tired. You'll be like, okay, I have traveled so far. I've had a lot of kinetic energy. I've used up all that kinetic energy. I became exhausted. And finally, I reached infinity. And I'm like, whew, done. Now I will no longer get attracted from anyone. So now I can have zero kinetic energy. Because if you have zero kinetic energy much before reaching infinity, much before reaching that very far distance, then gravitational force will again pull you back. Because if you stop before the gravitational pull disappears, that's it. Gravity will be like, hey, come back. You stopped, right? Come back, come back. It'll be like, oops, I have to go back. So if you stop at infinity, you don't have to go back because there is no gravitational pull. So your kinetic energy just becomes 0 at a very far distance. So that is 0. Is that understood, my warriors? Yes. Very good. Great. Wow, Strashti, glad you finished the miss part with 2x speed. Good that you caught up. Now move this around. Oh, by the way, m goes off and we have ve square by 2 is equal to gm by r. And then let's move this around and let's see what a beautiful world we have. And we will get v is equal to root of 2 gm by r. That's it. Done, done. This is the escape speed. So for escape speed for any planet, use this formula. G is gravitational constant, m is the mass of the planet, r is the radius. For Earth, it's roughly 11.2 kilometers per second. So if you throw something at 11.2 kilometers per second, it will not come back to the Earth. But that's an ideal situation because we have neglected Earth's atmospheric resistance. So the true escape speed is actually much higher than that. But let's discount that for now, because we are now preparing for JEE and we often neglect air resistance. So let's just discount it. Okay, so the escape speed is root 2 gm by r, and for Earth, using this formula, it comes out to be 11.2 kilometers per second. Okay, for Moon, it is very less. For Jupiter, it's much higher. And for a black hole, how much should it be? Come on, let's see how many of you can guess that answer. How much do you think it should be for a black hole? Wow! Glad to know that, Kalyani. Excellent. Chemistry exam was awesome. Very good. Proud of you. Okay, too high. Infinity? No. It will not be infinity. It just has to be speed of light. For a black hole, or for any object to become a black hole, to qualify it as a black hole, like you have a qualifying exam for clearing IIT. So, for any object to qualify as a black hole, what is the criteria? Escape velocity should be higher than the speed of light. Because nothing can travel faster than speed of light. Why do you want infinite speed? That's it. It will be like, the qualification criteria is speed of light. All the objects will be like, what's the use? I cannot exceed the speed of light. It's like saying, the qualification marks to get into IIT, okay, is 102 percentile. How is it possible? You cannot get 102 percentile. That's unfair, right? So that way there is a limit till which your speed can go. And that limit is speed of light, my warriors. Yeah. Glad Dinesh, Pandu and Champa are back. And here is the first question on your screen on escape speed. Come on, let's do this. Fatafat. Yeah. So light can't escape from black hole. No, Roshni, you know, there are beautiful things which happen on a black hole. Because light can't escape, you know what will happen? Light will do like a projectile motion. Yeah, you have a torch which is on black hole, it will go up, and you're like, oops, I cannot escape, and it will come back. Zoop. So the light will do a projectile motion on the surface of a black hole. Isn't that cool? Okay. Great. Let's move ahead. Kalani, that's what sometimes matters. You should just have the proper blessings. You should just have proper faith, and you should just have confidence on yourself. Everything else just slowly starts, fixing itself up, and it starts connecting itself, and you will see that you will actually do good in life. Yeah. So I'm so glad for all of you who have tremendous faith on this channel, or you have tremendous faith in me, and you are sincerely following all my classes either live or in recorded form, and you're posting all the answers after the session ends. Good. So let's do this question coming up on your screen, and here it is. The ratio of the radii of the planet A and B is L, ratio of acceleration due to gravity is m, the ratio of escape velocity from them will be. Okay, what is the formula for escape velocity? Escape velocity is root of 2 gm divided by r. But I don't have mass of the planet, instead I have acceleration, but I have radius. Acha, radius is there, acceleration is there, I need to get rid of some terms. I know what I can do, just multiply and divide by r. So this will become r, okay, I'll just write it again, root of 2 gm by r square, and again r over here to preserve the equality. Oh, I know what this is, gm by r square. You have seen this again and again. What is it? Acceleration due to gravity on the surface of the planet, which is g, and that r just comes over here as it is. So I think now I got what I should do. So escape velocity of 1 upon escape velocity of 2, when you take the ratio, 2 gets cancelled, it will be g1 by g2 into r1 by r2. Now is g1 by g2 given? Acceleration's ratio is m. Radius ratio, what is it? It is L. So that's it. The answer is root ml. Done? Done. Oops, the screen is flooded with option B. Proud of you, bacha log. Moving on to the next question. It is. Moving on. A body is projected from the Earth's surface with a speed equal to half the escape speed. Not escape speed, half the escape speed. So obviously it can't reach infinity. What will happen? It will go up. It will lose all its energy. It will be like exhausted. And it will come back. It will stop somewhere. So the question is, what's the maximum height it will reach? Let's solve this. Okay. Where are we? Let's draw a diagram, because diagrams always gives you a correct way of visualizing, and it gives you a proper way of approaching the problem. So we have a body which is projected from the surface of the Earth. Let's say this Earth has mass m, radius r, and what you have done is you have thrown this object with a speed v. It goes up, but not so much, height h, and it comes back. So at this point the velocity becomes 0. This is the maximum height. Great. I think I now know what to do. This is my initial point. This is my initial point, and this is my final point. I'll just use energy conservation, I feel, because that's how I can find out the height h, and all I'm going to say is initial potential plus initial kinetic will be final potential plus final kinetic. Done. Start doing this now. Initial potential energy. This point mass is here. Okay, this is a point mass here, and it is at a distance of r from the center of the planet. So just minus gmm divided by r. Okay, great. Kinetic energy half m escape speed by 2 square, because it is given, equal to half the escape speed. I'll substitute it later on. Is equal to final potential energy. Well, I know the total separation will be something. Let's just, for now, I'm just going to call this entire distance as x. This will be easy for me to solve. Later on I will find out that height. Okay, so minus gmm divided by x. Last thing, final kinetic energy will be 0 because speed is 0. Okay, let's substitute even more things, and before that let's also cancel few things like m and m from here, and I'll get minus gm by r plus half into this 2 square will be nothing but 4 2s are 8, so 1 by 8. Escape speed is root of 2gm divided by r whole square. Correct? That's the value of escape speed. Is equal to minus gm by x. Interesting. So now what do we have? I think when I square that, the root will go off and I will see a lot of things getting cancelled. Okay, but anyways, I'll just write it over here. Minus gm by r plus 2 by 8 will be 1 by 4. 1 by 4 gm by r is equal to minus gm by x. So many things are going off. Gm, gm, gm. Done, done are done. Bring that minus sign over here. So it will be 1 by x is equal to 1 by r minus 1 by 4r. So 1 by r minus 1 by 4r, 3 by 4. So 3 by 4r is equal to 1 by x. Naturally, x will be 4r by 3. But I don't need x, I need h. How much will h be? H will be x minus r. So it will be 4r by 3 minus r, which is just r by 3. And is that there somewhere? Yep, it is. Option C. Correct. No, it is not r by 2, it is r by 3. A lot of you got the wrong answer. Okay. Yeah, be careful. It is not r by 2, it is r by 3. Clearo? Understood? So see where you made mistake. See if it was a conceptual, was it a calculation mistake, or you guys made us just a big blunder while doing something else. Okay, so that's the answer. Okay, beautiful question. Now let's move on to the last question for today. And this is truly amazing, and let's see what it is. Let's say, okay, I'll ask you a simple question. Let's say you go near a wall, you climb that wall and you jump on the ground. Okay, let's say you jump on the ground. You will come down. Everybody agrees? Do you think the earth also comes up? Do you think the earth also comes up? Not relative to you. From outside frame, do you think the earth also comes up? What is your answer? Think. Yes, oops moment. When you jump, let's say you're standing on a tall wall and you jump towards the earth. Do you think the earth also comes up at least slightly? Might be negligible? Well, the answer is like this. Why do you come down? Because there is a gravitational force. You can clearly see yourself falling towards the earth. Why do you see that? Because that force produces a very good amount of acceleration. Because your mass is small, force is mass into acceleration, acceleration is force by mass. And because the mass is not that great and force is decent enough, you have a decent acceleration of 9.8 meters per second square. By third law, whatever force is acting on you, the same force should act on earth. Same force should act on earth. But now think, will the earth have that much acceleration as you did? Obviously not, because the earth is very massive. So the earth will have negligible acceleration. Hence, the earth moves, but it is so small that you obviously will discount it. It will be so small that it will be smaller than the size of the nucleus. So it doesn't really bother. I don't care. But I'll be worried if I was not as much as I weigh now. Maybe I weigh a lot more than I weigh now. Let's say my mass is around 60 kg now. Well, let's say I weigh 600 trillion tons. Like, sir, how fat will you look? I don't care. Okay. So imagine a Pandu who is 600, 700, 800 trillion tons. Now that Pandu jumps towards the earth. Now it will make a lot of difference. The gravitational force will be even stronger. M1, M2, G, M1, M2, M1, M2 product will be very strong. Now the earth will start moving. Pandu will be like, hello, wait a minute. Earlier I was small, you are big. Now even I am as massive as you are. Why should I listen to you? You also come up, I will also come down. So both of them will move significantly. And then the accelerations cannot be neglected. Then their displacements cannot be neglected. Then their velocities cannot be neglected. So that's what happens when two massive bodies collide. Both of them will move. Nobody will say, hey, I'm not going to move, I'm massive. The other will be like, hey, even I am massive. You also move, I'll also move. So that's what is going to happen in the next problem. Let's see this. Two stars, each of one solar mass is 2 into 10 to the power 30 kg, are approaching each other for a head on. Oh my god, that's going to be a big dhamaka. Both of them are coming towards each other. Oh my god, Roshni got a mild heart attack. Oops. Don't worry, Roshni. I don't think even if I eat 20, 30 gulab jamuns per day, I will never become that fat. Yep. Yeah, that will be bigger than a dinosaur. When they are at a distance of 10 to the power 9 kilometers, their speeds are negligible. What is the speed with which they collide? The radius of each star is 10 to the power 4 kilometers. Assume the stars to remain in undistorted form till they collide. Okay, fine, cool. I'll assume that. Sure, let's draw it. Let's get a feeling out of it. The radius is 10 to the power 4 kilometers. The distance is 10 to the power 9 kilometers. The distance is 10 to the power 5 times more than the radius. So, if this is the planet, if this is the radius of that planet 1, let's say the mass is m, this is the radius r, the distance is 10 to the power 5, 10 to the power 5, it's crazy. It's not 1000 or 10,000, it's 1 lakh, 1 lakh times more. You take this r 1 lakh times. Oh my god, it's going to go out of the board. Just for the sake of it, I'm just drawing it. This is highly underestimated. Please let me tell you that. So this is also r and this is m. So very, very far away. You can see that. That distance is crazy. It's as good as infinity. I mean 10 to the power 9 kilometers in comparison with 10 to the power 4 kilometers. It's massive. Great. And what is given? Their speeds are negligible. So they are moving but negligible speed. Okay, so I'm just going to say velocity is 0. Velocity is 0. Great. There is some small gravitational pull between them. And because of that gravitational pull, because the separation is not completely infinite, they will slowly start coming towards each other. When they come closer, force will increase. When they come even more closer, force will even increase. Now the distance between them starts reducing at a very fast rate. As they come closer and closer, force grows. As force grows, their acceleration grows. As their acceleration grows, you will see they will come and approach each other even with higher speeds. And they will have bang, dham, doom. It will be like a massive explosion. And that's what is going to happen. So eventually what you're going to see is, oops, yeah, let me draw it again. Yeah, so we have this mass. Okay, now you'll be like, sir, the planets became big. Okay, just ignore that. So this was initial situation. And now this is the final situation. Just before colliding, this has some speed v, this also has some speed v. The question is, what is their speed with which they collide? I know what to do. Energy conservation, obviously, right? Let's start with that. Initial potential, initial kinetic will be final potential, final kinetic. What is the initial potential energy? दक्ष, मैंने कब कहा कि KVPY पोस्टपोन नहीं होगा? I never said KVPY पोस्टपोन नहीं होगा. You do not know कि पोस्टपोन होगा कि नहीं होगा. So I just said till that time it does not get postponed. Assume the date was 7th November. I never said it will never get postponed. Okay? So because a lot of weird things are happening from the last year. You expect something, something else happens. There was not even one exam which happened on time. Whenever you prepare for something, it gets postponed, it gets cancelled. God knows. So just don't worry about it. Just prepare. The students who keep worrying about when it will get postponed, what is going to happen, nothing will happen with them. I mean, like, you will not concentrate on the core concepts. You will just be wondering about all the unnecessary things. So that's why I said, keep studying. If it gets postponed, we'll announce. And that's what happened. I announced it today. And now you have more time. Now use that time for preparing even better. Okay. Divya, I'm very good, bacha. So what is the initial potential energy? Yes, it is infinity separation. That means it will be 0. Very large separation. Because this value is very, very large. So ignore that. Initial kinetic energy 0. In final potential energy. Okay, these are like two masses separated by a distance of, check this distance. What is this distance? 2r, right? R plus r, 2r. So final potential energy will be minus GMM divided by 2R. Final kinetic energy, both of them have kinetic energy, don't ignore that. So half mv square into 2. Why this 2? Because both planets will have it. Both the planets or stars, whatever, they will have it. Okay, so take this guy on the other side. So gm square by 2r is equal to 2 gets cancelled. So mv square, m and this m gets cancelled. So v will be root of gm by 2r. That's it. Done, done, done. Now substitute the values. G is known, okay, m is known, r is known. Just substitute it and you will get the answer. And guess what the answer comes out to be? The answer comes out to be 2.58 into 10 to the power 6 meters per second. Massive speed. This is crazy speed, my warriors. 2.58 into 10 to the power 6 is just 100 times smaller, almost, than the speed of light. Very close to the speed of light, but not yet the speed of light. It's crazy. So that's why when they collide, it will produce massive energy. There will be a lot of dust, there will be a lot of storms, there will be a lot of quakes, there will be tukde, there will be asteroids, there will be broken pieces, lot of energy, lot of heat, lot of sparks, and that energy can produce even more amazing things. Lot of things will just get melted. Yeah, it will vaporize. So tremendous amount of energy will be created. How to join my coaching class? Sriram, I'll just tell you, wait for 2 minutes. Now I have few homework questions for you. This is the first homework question. Just put it up in the comment section below. Okay, this is the first one. The second one is this one, the escape speed related problem. Again, you can do it very easily if you have attended my class today. And the answers for this will be up on the Telegram channel. So there is a link in the description box to join the Telegram channel. So I'll just show that to you, and we'll also see the last times students who have answered all the questions. Where are you? I am here. This is lecture 1. Okay, so you can see there is a link for joining the Telegram channel. Join our Telegram channel. This is me on Instagram, and you will also get the PDF of every session. Okay, and you can join it from there. And last lecture we had Ishpreet, we had Vaishal, who loved it, and Pandu really fascinated him. Okay, Chandan, very good Harita, very good Gokulnath. Thank you Gokulnath for all your sweet comments. It really makes my day. Thank you. Simran is also very happy with the session, and yes, Simran, I'll be completing the chapter by tomorrow. Okay, Suchi, and then JD, UD. What's the difference between the classes? I think I explained that to you, and very good Ritu. Congratulations. Now, not just that, even in today's class, you will see that there is a link. Somebody was asking, sir, how to join my coaching? Very simple. See, do you see avail all exciting Vedantu courses by clicking the links below? The current video which you are watching, just go below in the description box. Just go below. Okay, you will see this. JEE 2 years. Click on this. Okay, something went wrong. Oops, what just happened? I think I'm not logged in or something. Okay, let me just try something else. Oops, I think, oh, is Vedantu also hacked today? I don't know. YouTube was hacked. Now Vedantu is also hacked. Oops, I don't know. Okay, so maybe a technical problem right now, but you can click on this link and it will work. Maybe try it after some time. It should work, okay? And that will enable you to join the courses. Now, what and all do you get in the courses? Let me tell you that. So first of all, you will get tests, you will get assignments regularly. Number 2, you will get lots of micro courses, including my micro courses. Not just that, you have an option to learn in English and Hindi, and most of our batches are in English, which is very good. Not just that, you have all amazing teachers just like me, even more experienced than me. Not just that, you also will get detailed report cards, you will have parent-teacher sessions, you will have guidance sessions, you will have interactive sessions, doubt-solving sessions, so many things apart from just coaching. See, JEE is not just about coaching, it's about all the other things together. That ecosystem should be there. So you might be wondering, what are the different packages that I get? So when you click on that link, you get 3 packages: Light, Classic, Plus. Whatever I just told, the classes, the recordings, tests, assignments, etc., you all get it in the light version. But most students go for the classic version because they want somebody to answer all their doubts after the class. So you get the doubt facility, unlimited doubts, no cap on that. And if you go for the plus version, you get the added benefit of a personal mentorship. That is a personal guide which will help you solve the problems. You might be wondering, sir, if you're giving so much, I'm pretty sure you'll be very expensive as compared to the normal coaching, which charges around 2 to 3 lakhs per year. Well, we don't even charge that for 2 years, bacha. In fact, our prices are negligible. So you can check it out, 1,350 per month. In fact, on the link in the description box, when you open that, it will give you 15-day trial. But on that 15-day, you get extra 15-day trial free with this coupon code SHHPRO. Not just that, you additionally get 10% off. So basically, you get a 1-month trial at a 15-day cost with 10% discount. That's a massive deal. Not just that, if you're very happy, you're like, sir, I want to join the entire course, that's even better. Take up the entire subscription, and you also have the option to pay monthly installments. So that option is also there for all of you. Okay, so I'll be really expecting all of you out there. And if you have enjoyed today's session, you know what to do. Yeah, if you're not yet subscribed, hit the subscribe button. If you feel a friend needs these kind of sessions, share this, recommend this channel. And yep, if you have already done that, do not forget to smash that like button down there. Alright, chalo. So practice all the questions and do the homework and post it up in the comment section below, because I'll be giving again a shout out in the next class, which is tomorrow. So tomorrow will be the last class before Diwali vacations, but I have already recorded few sessions for all of you so that you guys still stay engaged. And where do you think Shreyas Sir is going? I'm going somewhere out of Bangalore, and hopefully I'll be able to go live from that location. And where that location would be, well, you can take a wild guess in the comment section. I'll be really reading your chats. Take care, hasta la vista, have fun, stay safe, have a great dinner, spend a lot of time with your family during these Diwali vacations, and also use this time to cover up all your backlogs. Okay? Chalo, bye, take care, have fun. This was Captain Shreyas going live. Hasta la vista.